Continuing on with what we have in solving differential equations by series and summations. And we had, from the other day, we looked at first order differential equations. And we're going to cross over to just some simulations of working with second order differential equations. And again, you have just for your summations and series, again, we have for the general layout for y, okay, we have, again, the summation is n goes from 0 to infinity of c sub n times x to the n, and we have the expanded notation where we have this series of terms. And again, for y prime, okay, we have, again, the first order derivative of what we have in the series. So you have the first term at c sub 1 plus 2 c sub 2 of x, and so on. And for the second order derivative, okay, we have the general notation within the summation where we have n times the quantity of n minus 1 times c sub n times x raised to the n minus 2 degree. And we have in the general notation, okay, we have that, and as you write, going from 2 to infinity, and we have our first term in the layout, we have 2 c sub 2 plus 6 c sub 3 x, and so on, okay. And so for the expanding notation, so I'm taking the derivative of what I have in y, developing y prime, and then taking the derivative of that, I have, again, this series for the second order derivative. And looking at what we have with second order differential equations, and let's say that for a case, if we're looking at solving for y, where we have y double prime plus 4y is equal to 0. And I have the series very much laid out. Okay, so you have y double prime consisting of the term starting with 2 times c sub 2, and we have 4 times the quantity of y, where we have the series expansion where we had the leading term at c naught, and looking at combining like terms and setting to 0. So you have like 2 c sub 2, 4 c naught. Okay, those are going to be the only standalone constants. And we have 6 c sub 3 x plus 4 c sub 1 x. And if I just keep the constant portion, so I have 6 c sub 3 plus 4 c sub 1 equal to 0. And likewise, in second degree, in x, if I keep just the coefficient portions, so I have 12 c sub 4 plus 4 c sub 2, and continue on with the pattern for combining the cubes in x terms. We have the coefficients at 20 c sub 5 plus 4 c sub 3, and just setting these equations to 0. And we have for the leadoff, we have for 2 c sub 2 plus 4 c naught is equal to 0. We had that c sub 2 is equal to negative 4 halves c naught. And just like in the first order differential equations, we have been using factorials. And now there's going to be a pattern, okay, that's ultimately going to be constructed where we have right now c sub 2 is going to be equal to negative 4 over 2 factorial times c naught. And c sub 3, okay, you're going to have negative 4 6 c sub 1. And we're going to have negative 1 to the first times 2 squared over 3 factorial c sub 1. And for what we have for 12 c sub 4 plus 4 c sub 2 is equal to 0, I have c sub 4 is equal to negative 4 twelfths of negative 4 halves c naught. And right now I have negative 1 squared times the square of 4 c naught all over 4 factorial. And we have with c sub 5, okay, just looking at the pattern, we have just looking at expanding. So you're going to have negative 420 this times negative 4 6 c sub 1. And just looking at what we have in terms of the exponential base 4, okay, have repetition of the negative, so you have the square of negative 1 times the square of 4 c sub 1 over 5 factorial. And notice we have the factorials. We're taking that of numbers that match with the subscripted values. And if I create a pattern to where the exponential base in the numerator is going to be raised to the degree that matches the subscripted value attached to the constant. So negative 4, remember that is going to be the square of 2, okay, and writing negative 4, okay, and working with the exponential base 2, we can say that negative 4 is negative 1 to the first times the square of 2 c naught over 2 factorial. And now with c sub 3, now we have, again, the negative 4. We have negative 1 to the first times the square of 2. Now, if I write the base 2 to the third degree, what I can do is I kind of doing a little bit of borrowing. Like 2 squared would be 1/2 of 2 raised to the third. Just like 2 squared is 4, 2 cubed is 8, and 4 is going to be 1/2 of 8. And if I write the base 2 in terms of where it is raised to the third power, I can just kind of take a little bit of a sacrifice, okay, just extend a fraction on out with 1/2. So you have 1/2 of negative 1 to the first times 2 cubed times c sub 1 over 3 factorial. And notice for c sub 4, okay, I have negative 1 squared times 4 squared. And rewriting 4 squared in terms of base 2, that's going to be 2 to the fourth c naught over 4 factorial. And again, we now have a match between the power to which 2 is raised and the value of the factorial, okay, with 4 factorial. So you have a match. And likewise with c sub 5, okay, we have 4 squared again. That translates to 2 to the fourth. And to make this in 2 to the fifth, like what I did with c sub 3, okay, I upped the power by 1 by taking 1/2 of 2 to the next power. So I have 1/2 of 2 to the fifth. And we have a pattern that is going to be involved. And we're going to be doing a little bit of separating. And for the even values of n that we have, you got c sub n is equal to negative 1 raised to the n halves times 2 raised to the n all over n factorial times c naught. And for odd values of n, okay, notice we have the 1/2 jutting out. And we have like negative 1/2, or I should say negative 1 raised to the 1/2 of the quantity of n minus 1 times 2 to the n all over n factorial. Then we have times c sub 1. And if we look at separating, okay, the even from the odd and being able to consolidate. So if we let n be equal to 2k, okay, and just get it out of all these fractional exponents and factorial notations, we have for c sub 2k, from which we have c sub n. So if I replace n with 2k, n halves will be k, so we have negative 1 to the k times 2 raised to the 2k power. N factorial will be translated to the factorial of 2k. Again, we have times c naught, and for c sub 2k plus 1. And this is just to keep the subscriptive values odd. So we have negative 1 raised to the k, like 2k plus 1 minus 1 is 1/2 of 2k, so that's going to go to k. And you have 2 raised to the 2k plus 1, and the n factorial here is going to be the quantity of 2k plus 1 factorial. And again, you had the 1/2 out at the front. And again, we have, for this notation, you have c sub 1 as the constant being multiplied. And if we look at the solution we have for y, again, the standard we have n going from 0 to infinity of c sub n times x to the n, and then separating to where we have the even subscriptive values in one category and the odds in the other. And so for what we're going to have in consolidating, okay, so you have from c sub 2k x to the 2k, I'm just putting c naught out to the front, and I have the consolidated expression from c sub 2k, and I have times x to the 2k, and for c sub 2k plus 1, I'm putting 1/2 of c sub 1 out to the front, and I have times c sub 2k plus 1's factorial and exponential terms, multiplying x raised to the 2k plus 1 degree, and consolidating. Okay, so we have, notice we have both 2 and x are raised to the 2k degree. So I'm going to consolidate. And likewise for the odd series terms, or the odd subscriptive series terms, I have both 2 and x raised to the 2k plus 1 degree, and putting together. So I have negative 1 to the k for both of these. For the even, I have 2x to the 2k. For the odd, I have 2x raised to the 2k plus 1 degree. And notice in the denominators, I had the factorial of 2k and the factorial of 2k plus 1. And looking at what we have in the pattern. So for like 2x to the 2k over 2k factorial from what we have in the layout. Okay, this is going to parallel what we have for the cosine function, where you have -1 to the n, or in this case you have k. X to the 2n is symbolized by 2x raised to the 2k, and 2n where we have quantified and we're taking the factorial. We have the factorial of 2k, and so this is going to translate to c naught times the cosine of 2x, and we have 1/2 of c sub 1, and we have -1 to the k parallel to -1 to the n. 2x raised to the 2k plus 1, okay, is represented by 2x raised to the 2k plus 1. Okay, so x to the 2n plus 1 is represented by the quantity of 2x raised to the 2k plus 1. And we have all over 2k plus 1 factorial, again, running parallel to the factorial of the quantity of 2n plus 1. And that is going to be in reference to the sine function, where we have the sine of 2x. And that particular coefficient, 1/2 of c sub 1, you can substitute that out, okay, with different coefficient. Okay, so you can just kind of consolidate, and you can actually do the same thing for c naught, but 1/2 of c sub 1, you could go with something like alpha. So you can say c naught cosine of 2x plus alpha sine of 2x. And let's say that without changing things too much, if I have, instead of the sum of y double prime and 4y, if I take the difference, okay, and just in the expanded notation, so you have a bit of history to repeat, but where I had negatives before, I'm going to have positives. And so for c sub 2, okay, that is going to become 2 squared c naught over 2 factorial. And for c sub 3, okay, just like I had given up 1/2, and we have 1/2 of the cube of 2, c sub 1 over 3 factorial. And for c sub 4, that's going to be 2 to the 4th c naught over 4 factorial. And for c sub 5, again, I have 1/2 times 2 to the 5th c sub 1 over 5 factorial. And again, just like with the sum, I'm getting the degree to which 2 is raised and the factorial of the number we're trying to take to match the subscripted value alongside c. So for even values of n, we have c sub n is equal to 2 to the n over n factorial c naught. And for odd values, we have c sub n is equal to 1/2 times 2 to the n over n factorial c sub 1. And just looking at separating, okay, so if I let n go to 2k and had the odd values to be c sub 2k plus 1, this is what we have in the general layout. And looking at what we have and looking at solving for y, so I'm replacing what I have with n with 2k, and so you have on the even side, okay, just like what I did with the sum. So just moving c naught out to the front, and we have 2 to the 2k over 2k factorial times x to the 2k. And for the odds, again, just moving 1/2 of c sub 1 out to the front. And I have times the summation as k goes from 0 to infinity of 2 to the 2k plus 1 over 2k plus 1 quantity factorial times x to the 2k plus 1. And if I look at consolidating, okay, so we have c naught times quantity of 2x to the 2k over 2k factorial. For the even, I have 1/2 of c sub 1, and again, I have times the summation of 2x quantity to the 2k plus 1 all over 2k plus 1 factorial. And just looking at referencing what we have in the layout. So you have 2x to the 2k over 2k factorial, 2x raised to the 2k plus 1 over 2k plus 1 factorial. And just going back to what we have in the table. Okay, so we have... we're looking at the hyperbolic cosine functions, where I had x to the 2k over 2k factorial, and we have with the hyperbolic sine, okay, you have, instead of the variable to the 2n plus 1, I had 2k plus 1, and instead of the factorial of 2n plus 1, I had the factorial of 2k plus 1. But again, just regardless of the change up in the variable, you had the same logical pathway, and here you have x represented by 2x. And so we have, for the specific functions, we have y is equal to c naught times a hyperbolic cosine of 2x, and we have plus 1/2 of c sub 1 times a hyperbolic sine of 2x. And again, you can consolidate 1/2 of c sub 1 and throw in a coefficient such as alpha. And we're going to make a bit of a transition to Laplace transforms, but there is going to be a tie that's going to bind the concepts together, which I'll be presenting shortly, and that is going to be with what we have in the case of the gamma function. So we're still going to be preserving some of the notations involving powers as well as factorials.